Okay, folks, here we go. In the last video, you saw the three titration curves, and these three titration, say that 10 times fast, titration curves, had actually answered problem number 4, but indirectly. So if you look at problem number 4, it says sketch the titration curves for each of the following acid-base reactions, hydrochloric acid and ammonium hydroxide. That's a strong acid, strong base. This would be the curve for a strong acid, strong base, and the equivalence point at 7. For the second one, hydrochloric acid, strong acid, and methylamine. That's methylamine, the CH3NH2, and that is a weak base. So that would be represented by this curve over here on the right, where you would have the strong acid dominating in the equivalence point in the acidic range. Okay, we just replaced the NH3 with the methylamine on the bottom. So it's the same curve here on the right. And then, process of elimination, so you're smart people, you are. Then we know that the last question, 4C, which is the acetic acid and the sodium hydroxide, acetic acid, that would be a weak acid, strong base. The pH at the equivalent point of 9 or anything above 7 would be your equivalent point. And so that would represent that third part to that. So that's A, B, C to answer question 4. Okay, diving into question 5. Let's get rid of this. And let's do problem number 5. This is a titration problem. A titration problem deals with moles. Remember earlier in the last video, we said it's important that moles are going to be equaling moles to get the equivalent point. Moles of OH, moles of H. So it's all about the mole and how many moles of H's and moles of OH. Now that goes back to Chem 1. I told you from Chem 1, the most important thing you can learn in Chemistry 1 is the mole. Okay, that's important. But this is going to be a concentration problem because that's what we have. We have volumes and concentrations of solutions when we talk about titrations. So let's read that problem, problem number 5. A 0.2688 gram sample of a monoprotic acid. Now it just means you have one hydrogen on the front. It could be hydrochloric acid, it could be acetic acid, hydroiodic acid, whatever, it's just one H. Neutralizes 16.4 milliliters of a 0.08133 molar KOH solution. So we are neutralizing KOH, and is that strong? Yes, very good, very good, very good, Wanda. That is strong because we know that a hydroxide with a group 1 or group 2 metal on the front, strong. It's a strong base, which means it ionizes 100%. So what that does is this solution will give off, let's see, what was the concentration? 0.08133. 0.08133 moles per liter of this and 0.08133 moles per liter of this. That's the concentration, molarity. This one matters. That is your hydroxide. All right, and that's what matters in these acid-base titrations. This one doesn't matter, and this is just like bleh, so what? You're floating around, but who cares about you? You're not going to do anything to the solution. So that's what we're neutralizing. We're neutralizing this many hydroxides. How do we do it? We must have neutralized it by producing that many hydrogens. So we must have 0.08133 moles per liter of hydrogen to neutralize that. So that's where we start. So we got to start thinking about in terms of an OH is neutralized by an H, and however many of these I have, which was essentially, it was given right in the problem, is how many of these I have. I have that many hydrogens, and I'm going to need that many hydrogens in order to neutralize it. Okay, and let's say it's neutralized. So we did neutralize this with this acid. Okay, so let's see, what is actually the question? Oh, the question is, calculate the molar mass of the acid. Okay, that could be a little tricky. Let's see. Well, if I'm going to calculate the molar mass of the acid, if we remember back from Chem 1, that the moles is equal to how many grams of something you have, divided by its molecular weight, or you can say molecular mass from the periodic table. So for example, a little quick reminder that if I had 18 grams of water, H2O, when I looked up H2O on the periodic table, 2 hydrogens and an oxygen, I get 18. And so that would give me 1 mole of water. So that's how we calculated moles, and that's how we do calculate moles. So it wants me to calculate, it wants to know what the molecular weight is of this acid. So that's the unknown. Now how am I going to get that? I'm going to have to know 2 things. So I'm going to switch the molecular weight in the moles. I'm going to have to know how many grams of the acid, and I'm going to have to know how many moles of the acid that I used, okay? Because I'm going to have to know that. Okay, so let's see. Molecular weights equal grams per mole. I was given the amount of grams of the acid that was used. I was told that in the first line of the problem, the first number I was given, I remember that, 0.2688 grams of the acid. Now I just need to know how many moles of the acid that I use. Now this molarity is moles per liter. It's not the amount of moles unless I had a liter of solution. If I had a liter of solution, this would be the amount of moles per liter. But I don't have a liter. If I remember from the problem, it said blah, 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 acid neutralizes 16.4 milliliters of the base. So 16.4 milliliters of the base was the amount that I had. So if I go to my molarity, remember this? This is from week 2 of the course when we talked about molarity. It didn't go away. It's a concentration that has moles per liter. So what I want to do is all about the moles of hydroxide and the moles of the hydrogen. It's all about moles when it comes to these titrations. So I need to figure out how many moles of the hydrogen that I use so I can put that in here and solve the problem. Well, I know the molarity of the base. Now you might be just saying, wait a minute, you just said the moles of the hydrogen. Yes, I did, but we're going to get that by knowing how many moles of hydroxide, because every mole of hydroxide get neutralized by a mole of the acid. It told me that it's a neutral solution. So I can figure out how many moles of hydroxide, then I know how many moles of acid that I have. And I can put that in here and get this problem over. Okay, so let's go ahead and put some numbers in for this. I know that the concentration of the hydroxide, okay, is 0.08133. And I know how many liters of the hydroxide that I had. Now I have 16.4 milliliters, so that's 0.0164 liters. Take me to your liter. Okay. So if I multiply those, I know how many moles of hydroxide got neutralized. So multiplying these gives me the moles of hydroxide in the solution, and it told me I neutralized that, so I know exactly how many moles of hydroxide got neutralized, and then I know how many moles of hydrogen did it, because look at the same. 1 neutralizes 1. So multiply this out. Go ahead and multiply that out, and you get your moles equaling, okay, let's see, 0.08133 times 0.0164, 0.00133, 0.00133 moles of hydroxide got neutralized. That means that I used 0.00133 moles of hydrogen to do that. So I now know how many moles of hydrogen from the acid, how many moles of the acid that was used, that's what that means, how many moles of the acid, how many moles of the hydrogen was used to do the neutralization. Now that I know moles of the hydrogen, I can go ahead and put that down below. And that'll give me the molecular weight of that acid, because that's what the question was. It was asking what's the molecular weight of the acid that was used. I have the grams of it that was used, and now I've calculated how many moles were used, and that's the same amount to neutralize the hydroxide. So the moles of the hydroxide that I calculated is the moles of the hydrogen. All right, so do the math. Take that and divide it by that. So 0.2688 divided by 0.00133 equals 202. The molecular weight of this acid would be 202. And remember what your molar is grams per mole. So this would be grams per mole. Grams per mole. And that is how we solve problem number 5. When it comes to titration, it's going to be about how many moles is neutralizing how many moles of something else. So this concentration equation, the M is equal to moles over liters, comes back. And in this case, we had to go back and grab the moles equation. So we're using stuff earlier on in chemistry to help us solve a titration problem. All right, so that's problem number 5. We'll stop there, take a quick break. Whew. I'm exhausted. I'm talking like carbon dioxide, water vapor, nitrogen monoxide. Exhausted, get it? Because that's exhaust.